Hi, welcome back. We will continue with this second part of the lecture of today with Professor Cristina Garcia Vergara. Thank you very much for your participation, and Cristina, the space is yours.
Thank you. Then I'm gonna share my screen. Okay, I hope you can see all my screen now.
Yes, Cristina, we are seeing your screen.
Yeah. Okay, here then I'm showing like a summary of what we talked during the first part of this lecture. Just to repeat for those that are a little bit lost with the information, this is just a chronogram or a sketch about the history of the structure formation in the universe. We started the universe with a strong Big Bang. Then we passed through an inflation process in which the volume of the universe increased strongly and very fast. And after that, we have the CMB, the cosmic background, the cosmic microwave background, which is an observation of the matter density of the universe in the very, very early universe, in which we can detect already some inhomogeneities of matter. And then I explain you how these small inhomogeneities of matter grow over time. I explained you that this grow because gravitational instability of the sources, in which a matter over density has a little bit more gravity than the rest, and then this grow a little bit slower than the rest, and then become more massive with time. Then I explained that small overdensities become more massive with time, and small underdensities in the early universe become more underdense and less massive with time. Okay, so as I explained you, all this process in the structure formation is based on dark matter distribution, but I show you at the beginning of the class the distribution of galaxies in our in our local universe. Then we have a gap here between how these dark matter overdensities and underdensities turn into galaxies, right? Then that is the part that I will cover in this second part of the lecture today. So I said that overdensities are growing and growing over time, but this overdensity will not grow infinitely, and in which the radius will be enormous if you expect so much time, right? This growth will at some point will stop, and at some point a matter overdensity reach a certain critical overdensity, which is called critical overdensity, for which is a moment in which this overdensity of matter will start collapsing. Then this collapse finished as a dark matter halo. Then that is what we call dark matter halo. Of course, you can form different dark matter halos of different mass depending on this threshold on the critical density that you have. Then you will form some more massive halos or less massive halos if this condition is fulfilled before or after, right? Then what happens is, for example, if you take here one small overdensity in the density field, if this overdensity reach this threshold of delta C, a threshold of mass, basically the gravity will be strong enough there to win against the expansion of the universe, right? Then this force will start winning, and then the overdensity will start collapsing, but not collapsing up to one single point, because within this mass overdensity, you can find also small inhomogeneities, also between this big overdensity of matter. And that makes that dark matter particles will not collapse until a single point, but they will start orbiting, randomly orbiting around the center. Then this makes the halo don't collapse until one single point. If you will have a homogeneous distribution of matter within this overdensity, then you will expect that everything collapse in one point, but that is not the case because you have some inhomogeneities already within this overdensity. Then what happens is this will collapse until some point in which the sphere will be in equilibrium, in virial equilibrium. Then you will have dark matter particles orbiting within this dark matter halo, right? Of course, not all the overdensities will fulfill this condition at the same time. Then some dark matter halos will form before than others. And also that this was one question in the last part, in the previous part, the region in which this threshold of mass is reached first will become more massive first than the other regions, and then those will be the locations in which the more massive cluster of galaxies will be formed. Then basically the cluster of galaxies that we see in the universe today at redshift 0 were the locations in which the density field had the highest peaks at the early universe. Okay, and oops, sorry. And then, yeah, like to give you just like a definition of dark matter halo, dark matter halos are collapsed over densities in the dark matter distribution with a density which is around 200 times the mean density in the universe, inside of which all the mass is gravitationally bound. Then this 2000 number is more based on the typical amount of matter that a dark matter halo has when this reach their equilibrium. Okay, but then we still don't have galaxies here, right? Still everything is dark matter. Then galaxies will form in the center of these dark matter halos. Yeah, to understand how galaxies form within these dark matter halos, you will need to study galaxy formation models, and this will not be covered in this course because it's a very complex process. You have like different models and stuff, but I think that in some previous years you had also in this summer school someone that explained galaxy formation models. Then maybe you can check that. But the basic that you need to understand here is that within a dark matter halo, you will have a galaxy forming in the center of the halo, which is called the central galaxy. And almost all the dark matter halos contain at least one galaxy in their centers, okay? But also several dark matter halos also contain more than one central galaxy, which is, for example, the case I'm showing here. And all the galaxies that are not in the center are called satellite galaxies. This is just like a definition. Then, for example, a very known example of a dark matter halos with a central galaxy and satellite galaxies are the galaxy cluster that we observe in the local universe. A galaxy cluster is just that, a dark matter halo with a density around 200, the mean density of the universe, with a central galaxy and with satellite galaxies orbiting within the halo. Then now, when you map the position of galaxies in the sky, you are getting what I showed you in the very beginning, the distribution of galaxies in the space. Then you can already see that the distribution of galaxies is not necessarily exactly the same as the distribution of dark matter. Not even the distribution of halos is even not the same as the distribution of dark matter, because to form a halo, you need that dark matter fulfill certain criteria of mass. then the distribution of galaxies will be more or less the distribution of the dark matter in the universe, but it's not exactly the same. And that is why we call that galaxies are biased tracers of the dark matter. We will go more in details about this in lecture 4, but just for now, keep that in mind. Then I already mentioned this before. The mathematical description of the growth and evolution of a structure will not be covered in this course, but I just want you to understand some basic concepts in case you want to look for more details in books or something like that. I already explained you that all this evolution can be described using these 3 equations here: the continuity equation, the Euler equation, and the equation of Poisson, that are not linear. I already said that for the case in which the overdensities are not that extreme, you can ignore some terms in the equation which make it linear, and that is why it is called theory of linear perturbation, to describe all the evolution that I told before with these images here. However, when you already have formed a halo, your overdensity is not that tiny as before, and then you cannot ignore the terms in this equation as we did before. Then in this case, we talk about the nonlinear structure formation, because the equation that you have to solve to describe this process are not linear, and then are much more complex also to solve. You need to solve them numerically, and that is why the cosmological simulation need to be numerical if you want to include all the formation up to this point, up to this scale. Then when we talk about a small scale structure, which is the scale smaller than a dark matter halo, then we can only describe this using nonlinear structure evolution and nonlinear equations. This is just like for you to have this information. We will not go deeper in this in this lecture. Now, remember that I said that the universe is very inhomogeneous, but if you look at very large scales, you can see that the universe looks like homogeneous. Then that is what I want to show you in this animation. This is again a simulation of dark matter from the Millennium simulation. I'm going to show you the distribution of dark matter in our current universe, but I will show you like very zoom out, and then in the movie we are going more and more close to a certain overdensity in the density field. Then you can see here that is kind of homogeneous at large scales, but if you go to small scales, then to see the details of the structure, you start detecting that you have regions much overdense than others. For example, you have some regions without dark matter, and this region is very rich in terms of matter. Then this zoom into a node, one part of the filament that is very dense. And here we are zooming into a galaxy cluster, actually, into a region in which a galaxy cluster will be formed. This is more or less the scale of a galaxy cluster, the radius of a galaxy cluster. Then if we zoom out again, we can see all this detail in the structure of matter, but at very large scales, you can say that this is more or less homogeneous. Then, of course, the structure of the universe, the matter distribution, depends on the scale in which you are measuring. Okay, now I would like to convince you why it's important to study the large-scale structure and why it's important to trace and quantify it. Because visually, you can, if I show you an image of our universe, visually you can see, yes, I detect some structure, I see some filamentary structure, I can detect some regions without galaxies on it. But we really need a mathematical formalist to describe this level of inhomogeneities in the density field, right? And that is what I will define next lecture about how can we really measure the level of clustering and the distribution of sources in space. But why is important? Well, because this depends, the structure that we see today depend on several things. One of those is the initial condition that we had at the beginning, then basically the CMB, because in the CMB we already, we had the seeds of what will be the structure today. I mean, if you had like a tiny fluctuation in mass in the early universe, in the CMB time, then this will result in a structure which is different than if you will have a large matter contrast in the CMB, right? Then the initial condition is one important point of what we see today in the universe. Another important part is the cosmological parameters, because as you can imagine, all the growth of a structure that I explained you is basically a play between the gravity of one structure and the force that the expanding universe is making on that structure. Then you can already imagine that gravity models and the cosmology model, which basically controls how is this force given by the expansion of the universe, are very important parameters that impact strongly in which is the distribution that we see today, right? Then basically, if you have numerical simulations to describe all this process, you can assume different cosmological parameters, you can assume different amounts of dark energy, different forces that you are assuming in the universe, and you will get different results for the matter distribution in the current universe. Then basically, if you have different cosmological parameters and different models, you can compare with what we have observed today, and then the quantification of the large-scale structure that we observe today can be used to constrain cosmological models, for example, our cosmological parameters. Also, the large-scale structure that we see today depends on the formation and evolution of a structure. And particularly when you form galaxies and dark matter halos, you have to fulfill certain criteria that are not more so much dependent of cosmology anymore, but is more dependent on physical processes involved in the formation and evolution of galaxies. For example, the star formation rate, the amount of star that one galaxy has, the feedback that the galaxy produce, and how the environment affect the evolution of a galaxy. Then all those kind of things will impact in the resulting distribution of matter that we see today. Then if we can measure how the matter is distributed today, we can also understand what are the physical processes that impact in the formation and evolution of galaxies. Then summarizing this, the measurement of the large-scale structure in combination with theoretical models allow us to constrain both cosmology and physics of galaxy evolution. We really need both observations and simulations to understand the large-scale structure. If we only have observations, we cannot really interpret what we are observing. Then we really need simulations too, and also simulation require of observational constraint of the clustering to check and test which models are more more representative of what we are observing. Then this is very important to constrain, and large-scale structure teach us a lot about cosmology and physics behind the formation and evolution of galaxies. Then we will be talking in detail about how can we measure the large-scale structure tomorrow. But today, just to introduce you a little bit some concepts, the way that we use to quantify any deviation from a uniform distribution is to measure the clustering signal. When we talk about clustering, we are talking about how much grouped are the sources to each other compared with a uniform distribution. And the mathematical description of this is called the two-point correlation function, which is defined as I'm showing here, is C of R equal to the average of the overdensities in two positions X and Y. Then in this case, you can already see that this is based on how strong or how much is the overdensity in two different points of the universe. And you compute the average of that, and that gives you the two-point correlation function. Then basically the two-point correlation function measure how far we are from the uniform distribution, right? Because delta here show you how far the matter density is from the average in the universe, right? Then when you take two different positions and compute how far you are from the average, you can get the clustering or the two-point correlation function of the sources that you have. We will go much in more detail tomorrow about this. But one important thing that I would like you to keep in mind is that the measurement of the clustering of a population or the measurement of the two-point correlation function ultimately teach us about the dark matter halos in which galaxies live. And in particular, if you measure the two-point correlation function, then you can compute or determine what is the halo mass in which that galaxy or whatever the object that you are measure the correlation function, in which halo reside. Then you can obtain if this the mass in which the halo the object reside. Then that is a very, very powerful tool that we have to check what is the mass of the halo in which a galaxy is living. And that is really, really important. Then for the next class, I will be talking much about clustering. I will define it. I will explain you how can we measure this. I will explain better what is the two-point correlation function and how can we measure this directly from observations. Then I'm gonna make a very practical guide to measure clustering from observations. And actually in the workshops in the afternoon, well, my afternoon, your morning still, we will perform a measurement of the clustering of a population. Then you can, at the end of this week, you will be able to measure the clustering of a population. That will be, I think, very useful for your future too. Then in the next class, I will provide all the information that you need to measure this using observations. Okay, then.
Hi, Christina. Yeah. You have a question in the chat. Is there any lower limit for the distance between point X and point Y to be defined as two different points in the universe?
I guess it means that to this equation, no, you actually, I will show tomorrow that you can actually measure the two-point correlation function starting at very, very small separations, even at 1 or 2 arcseconds. If you take separation of 1 or 2 arcseconds, you already can start measuring the 2-point correlation function. Then there is not any like minimum distance of these points. I think that is the question, right? Did I answer the question? I hope so. But we will see this in more detail, because also, as I mentioned, the clustering also depends on scale. Then this is the R that which you see here. R is the distance between X and Y. And we will see that actually at smaller distance, the clustering signal is much more stronger. Then we actually need to measure clustering at small scales than at 2 very close separations. Okay, and now I have prepared a Kahoot. I know that last week some of you were also attending the lecture from Aurora, and she also was using Kahoot, and I hope you are familiar with this. For this, you have to, I have this here. I hope you can join me. You have to open Kahoot and use the pin that I'm going to show here. Oops. Yeah, here we go. Then I will be waiting for you to join us for this Kahoot. Then please participate. I'm gonna show 10 different questions just to check that you are following the lecture and how much did you learn. And probably I can explain you better based on what you learned here. I'm gonna wait a couple of minutes, then people have time to join us. If there's still people joining, I'm gonna wait a little bit more. Okay, I think we can start already. So here we go. Okay, first question. What do we mean with large-scale structure of the universe? One, all the structures inside of a galaxy, all the structures larger than a galaxy, all the structure larger than a galaxy cluster, or all the structures in the early universe. I think maybe all of you already replied. I just use a long time because of the delay. But great. Most of you gave the correct answer. The large-scale structure is all the structure larger than a galaxy. As I said in the beginning, several people said that all the structure larger than a galaxy cluster. Well, that is not true. Large-scale structure is everything larger than a galaxy, and remember that a galaxy cluster could contain several galaxies sometimes. Then the blue one is the correct. Okay. This is a true or false question. The universe is homogeneous at very large scales. True or false? Okay, great. Most of you got that part. Yes, the universe is homogeneous at very large scales. You can imagine this like as if you zoom out from in the universe, you can see that everything is more or less homogeneous. You cannot distinguish very well that you have like more dense and more underdense regions. But if you zoom in and see this at very close, then that means small scales. You can start like realizing that you have much more matter in some parts than others. Then that is good that you got that point. Okay, this question number 3. What is the observational proof that small inhomogeneities existed already in the early universe? The Big Bang, the inflation, the cosmic microwave background, or the distribution of galaxies in the Sloan Digital Sky Survey? Okay, great. All of you got it. That is fantastic. Yeah, and then yes, the cosmic microwave background is the observational proof of inhomogeneities in the early universe. The distribution of galaxies in Sloan is also a proof of inhomogeneity, but that is in the current universe, in the local universe, not in the early universe. Then great. Let's go for the next one. This is a true or false. A small underdensity of matter in the early universe will become more massive over time. True or false? Okay, probably the 90 seconds is too much time. Then for tomorrow, probably I will decrease this because I saw that most of you already replied this question. Then I'm still learning about this time because it depends on the time delay of the streaming too. Then sorry for waiting too long after each question. Okay, well, there was 8 people replied this incorrectly, actually. A small underdensity of matter in the early universe will become less massive over time, actually, because the matter there, well, how to explain this? Yeah, I already said that a more massive, an overdensity of matter will have more gravity, then it's attracting more and more matter to it, and the expansion of the universe is going faster than the expansion of this sphere of matter. But in the case of underdensity, this is in the other way around. Then you have an sphere with less mass here, then the expansion will be faster for this region, and then you will have a little bit less gravity there. You are attracting less matter around, and then at the end, this becomes less massive with time because particles are not attracted because you don't have so much gravity in this region. Then that is why an underdensity will become less massive over time. Okay. Next. This is a true or false. All the dark matter halos formed at the same cosmic time. Okay, 9 people replied this correctly. All the dark matter halos form at the same cosmic time. No, that is false. We will have some dark matter halos that will form earlier in time because it depends on in which moment an overdensity reach a certain critical overdensity for which this can start collapsing. Then if we had one place in the early universe that was much more overdense than the other, this will become more overdense much faster than the others, and will get this condition of the critical density faster than a different cosmic time, and will start forming halos before. Then we will have some dark matter halos forming at very early times in the universe, and we will have some dark matter halos forming just now at redshift 0. Then, yeah, this form at different cosmic times. Question number 6. When an overdensity of matter starts collapsing, what avoided to collapse infinitely until one single point? The force due to the universe expansion, the gravity in the overdensity is not strong enough, the inhomogeneities of matter within the overdensity, or the overdensity actually collapsed until one single point. Okay, we got different answer for this one. The correct one is the inhomogeneities of matter within the overdensity. Because when a overdensity of matter start collapsing, that is because the gravity is already very strong there. Then actually the gravity is strong enough to make it collapse until a single point. The force due to the universe of expansion start trying to avoid the situation, but at some point the gravity is too strong than the force from the universe expansion is not enough to avoid the collapse. However, what avoid the collapse is that we have small inhomogeneities of matter within the halo. Then that makes that the dark matter particles start having some orbits that are not completely radial toward the center, but start orbiting inside of the dark matter halo. Then that is actually the reason why this don't collapse. If you will have a halo which is completely homogeneous, then it's the same matter in the entire halo, then you will have a halo collapsing onto one single point. But that is not the case. Good. This is a true or false. Dark matter halos can host more than one galaxy. Okay. Yes, true. Great. Only one of you was wrong with this one, but yeah, dark matter halos can host more than one galaxy, and one typical examples are galaxy cluster that we see in the local universe. Question number 8. What are the satellite galaxies? Galaxies orbiting around dark matter halos, galaxies residing in the center of each dark matter halo, galaxies orbiting around galaxy clusters, or galaxies residing inside of dark matter halos but not in the center. Okay, great. 10 of you replied this correctly. Satellite galaxies are galaxies residing inside of dark matter halos but orbiting around the center, not in the center. And the galaxy in the center is called central galaxy. Question number 9 is a true or false question. And it said, the detailed shape, density, and distribution of the large-scale structure only depends on cosmology and gravity. Okay, wow, 7 and 7. Well, that is actually false because the detailed shape, density, and distribution of large-scale structure also depend on the physics behind the galaxy formation and galaxy evolution, and also depends on the initial conditions, which is given by the CMB signal. Then the shape, density, and distribution is actually a very complex to understand because you have a lot of different factors impacting on what we see today. And that is why this is false. Next one, and I think this is the last question today. Measurements of the clustering of galaxies allow us to determine the halo mass in which galaxies inhabit, constrain cosmological parameters, understand how galaxies evolve over time, or all of them are correct. Okay, tomorrow I'm gonna give you only 60 seconds to respond the questions, because I checked that the time delay is only 30 seconds, then you can get 30 more seconds to actually think on the answer. Then tomorrow this will be more straightforward. Great, all of you got this point. That is nice. Yeah, because we will be talking about each of these things during the week. How can we interpret clustering measurements? How can we measure the Hill mass given a clustering? Then great that you already know that measurement of clustering is really useful. Okay, then Jamie, good, you're the third one. David, you're the second one. And the winner, Juan. Oh, great. Congratulations, Juan. Yeah, in general, all of you were following pretty well the lecture. And I'm glad that I was clear. Today, the lecture was kind of smooth, qualitative. Tomorrow will be a little bit more mathematic and more technical, but still not that much. Then I will just finish with this.
Excuse me, Cristina.
Yeah, sure.
You have a question in the chat.
Yeah.
Regarding question number 9, what does it mean for it to quote depend on cosmology?
Okay, let me check what was the question 9.
Yeah, I don't remember either, sorry.
I think I have it here. Question 9 was, okay. The detailed shape, density, and distribution of large-scale structure only depend on cosmology or gravity. With only depends on cosmology, I mean that the shape that we see today just depend on how much force is doing, for example, the expansion of the universe. That is, I mean, cosmology define the cosmological parameters, which is basically the density of dark energy, and dark energy is basically the main parameter that control how much force you will feel because expansion of the universe. Then that is what I mean with depend on cosmology, only cosmological parameters. But also gravity, for example, is not cosmology, and gravity is also making a job, trying to put everything together, and physics, physics behind the formation of galaxy, for example, that is like baryonic matter. That is not cosmology. Then cosmology is just what controls the whole behavior of the universe. Then that is what I mean with depend on cosmology. Okay, then I just want to show you the take-home message of the class today. Because the answers in the Kahoot, I got that most of you got the main message, but I will just repeat here. Gravitational instability leads to an increase of density fluctuations with increasing times. Overdense regions become more overdense, and underdense regions become more underdense. Then at some point, when the overdensity is massive enough, it collapses to form a dark matter halo where galaxies can form. Measurement of the large-scale structure in combination of theoretical models allow us to constrain both cosmology and the physics behind of galaxy evolution and formation. Finally, we quantify large-scale structures through the measurement of the clustering of galaxies, and mathematically this can be described by the measurement of the 2-point correlation function. Then here I'm just repeating the two important equations that I showed today. And yeah, and that is all for today. I really enjoyed the class. I hope that you also enjoyed the class. We will have a workshop in 25 more minutes. I really encourage you to come. As I said before, sorry, let me stop sharing. As I said before, this week in the workshop, we will try to measure the clustering of a population of galaxies, actually. Then you can really have that skill at the end of the week. Then we will start today working with a catalog and playing a little bit with the catalog. And tomorrow, after I explain the basics of clustering, we will start working in the clustering measurement. For this workshop, it is needed a basic level of programming, but I guess that most of you can make some codes. You need, I don't know, cycle for, cycle if, not so much more complex than that. Then I hope that everyone can join me and learn about clustering and large-scale structure in 25 more minutes.
Thank you, Christina, for the lecture. It was very interesting. Let's see what is coming for tomorrow, because the mathematics behind these are very interesting. So thank you very much, and see you everybody in 25 minutes at 10:25 Colombian time. You can arrange in different regions at 4:25 Christina's time. So yeah, thank you very much. Yes.
Also, before to forget, I will send by email, or maybe Esteban, you can send the email with the workshop for today. And also, I'm gonna put this in the website that I show at the beginning of the class. Then
yes, I shared the web address, the link. I shared it with you. I can share it again if you give me a second, where Christina has been putting all her lectures and all the
I will put it on. It's not yet there, but I will put right now.
Okay. So I saw there was the lectures were there, then the workshop is also there. So I will post it right now on the chat so everybody can access to it. Great. And yeah, Christina or me will send the workshop for today. So you will receive it in the next couple of minutes. So we hope to see you in 25 minutes. Thank you very much, all of you. And thank you, Christina.